x approaches negative infinity from e to the x is indeed 0. We see that. Look at the graph. Follow the function, follow the function, follow the function. So indeed is 0. So y equals 0 is a horizontal asymptote at negative infinity only. Perfect. Now look again at the graph and tell me what to write for the limit of e to the x as x approaches infinity.
0 to 0.
Okay, so let's follow the function. I have my little rock. So the rock will follow the function. My right finger here, from my right hand, my pointer here will be on the x-axis.
Infinity.
Thank you very much. Perfect. When I talk about this, this is not the graph of e to the x. The graph of e to the x is always increasing. Examples here will be 1/2 to the x, 1/3 to the x, but this is not what we are talking about. This is a different graph, a different function, with the base not e, which is 2.7 blah, 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 and it's not 10. So these numbers are bigger than 1, that's why they're here. These numbers are smaller than 1, that's why they're here. So the function is decreasing for these, not for that, or base 10. Okay, so now I would like to graph the inverse function, but I'm not going to put them here because I already have enough on those graphs, but I'm going to graph these two functions again so we can graph the inverses. Okay. So please carve these in stone. These are very important functions, please. So I'm going to graph both functions again. So this was the ugly one, so to speak, because we've been through it. And this is nicer. Okay. And now, in order to graph the inverse functions, first I have to graph y equals x. I cannot graph the inverse function before I graph y equals x. Y equals x is not going to be part of the graph, but it has to be graphed before I put in the inverse function. So now I'm going to put in the inverse function. Let's see if this is better. Symmetric here means this. Symmetry with respect to this line. The function and its inverse have to be symmetric with respect to y equals x. So if here we graphed e to the x, this function is natural log x. They are the inverses. They're inverses of each other. Same thing here. Notice that this function does not cross y equals x, but this one does. That particular point must belong to both, because I can reverse it. It's the same. If it's 1, 1, of course it's not 1, 1. But if it's 1, 1 on y equals x, 1, 1. 1, 1, when I reverse it, it's still 1, 1. So here's the graph. So if this is a to the x, not e, of course, it has to be 1/2, 1/3, 1/16, 1/5, 1/7, whatever. Then this will be log base. It has to be the same base. Otherwise, they will not be inverses of each other. Is this clear? Of course, if this is 0, 1, this will be 1, 0. And it has to be. So this is 0, 1, and this must be 1, 0. Same thing here. This is 0, 1, this is 1, 0. So please remember these functions together. We're more interested in this. So now I'm going to ask you the limit as x approaches 0 from the right of natural log x, and the limit as x approaches infinity from natural log x. So look at the graph. Is this color okay? Is it visible or not?
I can see it.
Okay, thank you. So can anyone give us those limits?
The first one, negative infinity.
Excellent. We follow the function, my little rock. So here it is. As x approaches 0 from the right, maybe I should have done it differently. How do I do it? I don't know how to do it, so I don't cross my fingers. Yes, awesome. That's it. Which means x equals 0, a vertical asymptote. Perfect. Now, anyone? Anyone?
0.
Okay, let's follow the function.
Infinity.
Thank you. Good. Which means nothing. Okay, so let's take a look at properties of log. Any log in any base has these 4 properties. Log from a product, log from a ratio, log from a power, that's B, and the change of base formula. Yes. Log of a product, and there is no other function that has this property. Log of a product is the sum of logs. Log of x plus log of y. Log of a ratio is the same, but with minus. Log of the top minus log of the denominator. This one is the easiest. You move b in front as a factor. Factor. Factor means multiplication. So b times, not plus, not minus, plus, times log x. And the change of base formula. If we have any base, we can change it into any of the 2 in the graphing calculator. So if I have, let's say, log base a of x, and I want to change it into either natural log or log, common log. I forgot to mention that. Let me write this down. So natural log x is natural log, and log base 10, which I showed you in the calculator, this is common log. So natural log is natural log. This is called common log, which means base 10, but we don't write it. We know that if there is no base, it must be base 10. So if I want to change this, I will change it to either log, common log or natural log, because that's what I have in the calculator. So this is a ratio, not to be confused with this. This says log applied to a ratio. This one is log of the number over log of the previous base, or the same thing with natural log. Please do not confuse this with that. This is one log applied to a ratio. These are 2 logs, one divided by the other. Okay. So I think we should, with all the information we have right now, we can answer a couple of questions from these pages. I'm sharing my screen. Where is it? Where is my book? Here's my book. No, that's not my book. Here's my book. Okay. Oh, I have a chat. Do I have to do something? Oh, okay. Thank you. Okay, where am I? I thought it was 201. Oh no, it's 203. 203. Okay. So remember, we even had this on, I was pleased to see that everyone did the compound annually, monthly, whatever. I only chose one. So there is no need to do this again. But now I want to talk about continuously, okay, which we did not have before. I mentioned it when we talked about it, but now I'm going to mention it again. So compound interest n times per year. Everyone did this correctly. A principal, the accumulated value is the principal 1 plus r over n raised to nt. I think almost everyone did this correctly. So this is for compound interest n times a year. But now we can talk, because we couldn't talk before. Now we can talk about compound interest continuously. So continuously now. So this was what we just did in chapter R. Continuously. Same formula, kind of formula, A equals P, but E to RT. And now we know what E is. R, same thing, annual interest rate. T is the same thing, the number of years. P is the principal and A is the accumulated value. So I would like us to use this formula. You choose whichever you want, so we can move on from this.
What was E one more time?
Say that again.
What was E one more time? Is that just
right here? Right here.
okay?
Or this. This is E. This is Euler's number. When you click enter, you'll get 2, 4, 6, 9 decimal digits for E. Let me write this down for you. So E equals 2.718281828. It's Euler's number. Very good question. Let me explain a few things about this. So this mathematician looked at real life models, like bacteria growth, like cooling of a object taken out of the oven, and so on and so forth. So, and he tried to, through data, studying the data, he tried to fit different data points with a model, and he tried, I don't know exactly, I'm just explaining how the idea. He tried 2 to the x, it didn't work. He tried 4 to the x, it didn't work, and so on and so forth. He tried x cubed plus whatever, a polynomial function, and so on and so forth. And at some point in time, he realized that a lot of real life situations need a base to be not 2, not 4, not 3, not polynomial, but he came up with this number many times. So that's how the same idea was with pi. What did they do to discover pi? They took a circle and they measured the circumference somehow, and they measured the diameter. They took another circle, they measured the circumference and the diameter. They made another circle, they measured the circumference, and they measured the diameter. And when they realized, what they realized was that the circumference was always 2 pi times r. So they divided the circumference by twice the radius, which is the diameter, and they always got this number. For this circle, they got this number. For this circle, they got also the circumference divided by the diameter, and they got this number. For this circle, they measured the circumference, they divided by the diameter, and they got this number all the time. That's how he came up with this number, through trial and error. And he said, okay, well, this is the key. This is something super important that we should know about, like this pi. This pi is just a name given to, and you can always determine it. Your calculator will give it to you, 3.14, blah, 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 blah. Here it is, second pi. I'm not saying you need it for this class, but that's how you get it. So they named it pi, or something that they considered it convenient, because it appeared all the time. They couldn't get away from it. And they said, well, gee, this must be important. The same thing with Euler's number. He discovered it. That's why it's a little e that stands for his name, the first letter of his name. Very good question. Thank you, thank you, thank you. Okay, so he said, oh, this is so important because it appears in real life models all the time. So then they named it this, and now we know it represents that. Okay, perfect question. Thank you so much. Okay, what was I doing? Where was I? I was here. Okay, so let's choose and just plug it in, any of these 9 through 16, and let's plug it in.